time to do some more practice involving series, and in particular with an emphasis on geometric and telescoping. And so we're going to be doing lots of things such as identifying what kind of series we have, some basic manipulation, ways to simplify what we want. Everything that we do gets easier the more that we practice. That's why we want you to practice. The more that you practice, the easier it becomes, as with any skill that you're interested in learning. So keep the practice up. And if you're following along with the video, make use of the pause button. When you see a problem that looks interesting, try it yourself first. See how far you can get. But if you ever need any help, no worries. I'm always here. Just need to unpause me, and together we'll figure it out. Well, let's begin. Our first problem. So, two-parters. For which values of x positive does the sum x over 2 to the n plus 1 over x to the n converge? Now, the second part says, okay, suppose you have such an x, what does it converge to? All right, well, let's think about what's going on here. Okay, so our sum, we have n equals 0 to infinity, and I can really think of it, look, there's really two parts here. So I'm going to think of it as, really, I have an x over 2 to the n, and then there's another sum, n equals 0 to infinity, of 1 over x to the n. Now, in some sense, it feels a little strange here because we have an x, which we think of as a sort of like, isn't that like a variable? And eventually later on, we'll think of it as a variable. But for right now, you should say it's just a representative of something. So x is a stand-in for something we don't know. And so, all right, let's think about what we have. Well, we have a geometric series. And there's a basic rule about geometric series. So what's our basic rule? Our sum of a r to the n from, doesn't matter where we start, to infinity, this converges, and that's what we want to know, if and only if, and so if what? Well, if what we multiply by at every stage is small. So as long as we're multiplying by small so that the terms really shrink down very quickly, some might say exponentially quickly to 0, then life is good. So we say, aha. We just have to identify the right r's for these geometric sums. Well, we can spot them. So here, the first term is x over 2. Here, the second term, it's 1 over x. And we are assuming x is positive, so when we talk about absolute value, we can just simplify things. So what do we have? We need absolute value of x over 2 to be less than 1 for the first sum to converge. And we need to have 1 over absolute value of x, or really absolute value 1 over x, has to be less than 1. But as we said, x is positive, all right. So we need just simply x over 2 to be less than 1. The absolute value does nothing. 1 over x has to be less than 1. And if we multiply, what happens? Here, we would say, aha, this is the same as saying, look, we need x less than 2. And here, if you multiply, we would say x has to be greater than 1. So as long as x is small enough, then x over 2 is small enough, things converge. On the other hand, here, as long as x is big enough, then 1 over x will be small, so it will converge. So the answer for part 1, well, we need both things to converge. So it's going to be 1 less than x less than 2. So anything between 1 and 2, that will converge. Okay, so part 1 is done. Now, what about part 2? Well, it says, hey, now what does it converge to? So for instance, we know there's numbers. There are numbers between 1 and 2. Actually, there's a lot of them. For example, 1 1/2 or 1 1/4, right? There's a whole bunch you can make. Well, what does it converge to if we use that particular value of x? All right, well, what do we see? Well, we have geometric sums, and we know how to add geometric sums. The rule is you take the first term, well, n equals 0 means you get something to 0, which is 1. something 0 is 1. So, all right, so the first term in both cases is 1 over 1 minus what you multiply by. Here it would be x over 2. The second, 1 over 1 minus 1 over x. All right, well, we can clean this up a little bit. So, for instance, if you multiply top and bottom in the first one by 2, this becomes 2 over 2 minus x. Here, if you multiply by x, you would get x over x minus 1. And, well, let's go ahead and add these together. This would be 2 times x minus 1 plus x times 2 minus x over 2 minus x times x minus 1. In other words, we've got a common denominator. And, well, I don't know if anything simplifies, but might as well try. That's 2x minus 2, and then plus 2x minus x squared. Divide by 2 minus x, and x minus 1. And so, well, not a lot of simplification, but we get minus 2 plus 4x minus x squared. Divide that by 2 minus x times x minus 1. And that's it. We're done. Great. Beautiful. Beautiful. So now you give us any number between 1 and 2, and we say, look, that sum becomes that. Exactly that. And we're done. Wow. Good. Great. Well, that wasn't so bad. See, these sums, they're not so bad. It's something that can even be fun, right? Oh, yeah. There'll be some more jokes like that, I suspect. Find the value of the sum 1 to infinity, 2n plus 5 factorial minus 2n plus 1 factorial. Divide that by 2n plus 5 factorial times 2n plus 1 factorial. Wow, lots of factorials here. Okay, so what do we do? Now, our mindset when we see a problem today is if we see the word find, we're thinking, oh, this is asking for something that's either geometric or telescoping. Geometric is easy to spot. We always look for an n up in the exponent. So if we see an n in the exponent, and that's the only n we see, then we're like, ooh, geometric, nice. There's no n in the exponent here. So it's like, okay, probably not geometric. But there's something here which is signaling, hey, whoa, wow, look at this. This could be telescoping. Now, when we think telescoping, what we think of is we're adding things where there's a subtraction involved. So we're adding two terms in each piece, and the two terms are similar, but they're offset. So that when you look at the pieces together, we say, oh, something here cancels with something there, and then that's happening all the way down, and so you get this sort of collapse. So we think, oh, okay, because of that minus, it's a clue that it might be telescoping. I probably think it is telescoping. All right, well, let's keep digging, right? Go a little deeper. Now, what can we do? Well, we can break this up. Really, let's separate this. So this is the sum from 1 to infinity of 2n plus 5 factorial. Downstairs, it would be 2n plus 5 factorial, 2n plus 1 factorial, right? Minus, and then 2n plus 1 factorial. Downstairs, 2n plus 5 factorial, 2n plus 1 factorial. Now, at this stage, we're not going to be like, ooh, let's break it up into two sums. That's not how telescoping works. Keep it as one sum, but we say, all right, our goal is simplify. We say, hey, wow, 2n plus 5 is there, the 2n plus 1 is there. They're canceling out. Oh, that's great. So what we really have going on here is this is the sum from 1 to infinity of 1 over 2n plus 1 factorial minus 1 over 2n plus 5 factorial. And now we're like, hey, this is pretty promising. It looks like something, and it kind of looks like a very similar thing being subtracted, but off by a little bit. Now, if you look at 2n plus 5 factorial, what is that telling us? Well, we'll come back to this in a second. Let's maybe write down the first couple terms and see what's going on, because oftentimes that's very helpful when you're doing telescoping. So remember, we're starting at 1. Always pay attention to where you start. If you get into the habit like, oh, everything starts at 0 or 1, then someday they're going to start at 3 and you're like, what? I missed that. No, pay attention. We don't want to lose points for silly reasons. We want to lose points for really interesting reasons. Okay, so starting at 1, this would be 1 over 2 plus 1 is 3 factorial. And here it would be 2 plus 5 is 7 factorial. Okay, next plug in 2. 1 over 5 factorial. And then here, it would be 4 plus 5 would be 9. 1 over 9 factorial. And now, the next term, well, that would be n equals 3. 1 over 7 factorial. And then minus 1 over 11 factorial. And now, the next term, well, okay, we'll do a few more terms here. But hopefully, we're ready to say, okay, do we see what's happening? And do we think it is what it should be? Well, we should, when we look at it, say, ooh, check it out. This 1 over 7 factorial and this 1 over 7 factorial cancel. Don't have to make the noise, but if it helps, do it. Okay, and this 1 over 9 factorial and that 1 over 9 factorial cancel. And 1 over 11 factorial similar. And so forth and so on. Now, let's point something out here. Notice we didn't cancel right away. We canceled 2 terms later. Now, how could we have seen that that should be the case? Well, if you come back to the sum, we could have written it in the following way. 1 over 2n plus 1 factorial, all right. And then the next piece could have been written as 1 over 2. And then I'm going to write this as n plus 2 plus 1 factorial. Now, where am I getting this n plus 2? Well, I want to say it's like 2 times something plus 1. So I say, okay, how can I write 2 times n plus 5 as 2 times something plus 1? It's like, well, I got to take the 5. I'm going to have a plus 1 left over. That leaves me with 4. I got to move in. So 2 times 2 is 4. Now, here's the thing. You'll notice, I think you're seeing it, right? That plus 2, that's the offset. That tells you how far down you have to go to get cancellation. See? We had to go 2 down, 2 down, 2 down. And so what it tells you is that if you have to offset by 2, you're going to have the first 2 terms don't get canceled at the start. Now, what you have to be careful of is, what about the last 2 terms? Well, you might say, okay, it keeps going forever, right? But when we're doing our telescoping, we always have to say partial sums. And what happens to the end? So now, the other thing to observe is what's happening to that value. That value will determine whether or not we have to worry about the end. In this case, as n gets large, this is going to 0, which means that the little piece on the end, if you go far down enough, you can say, okay, look, these terms here at the start didn't cancel. These terms at the end, which haven't canceled yet, are very, very small. And they're getting smaller. And therefore, they go away. So, what are we left with? Well, we're left with 1 over 3 factorial plus 1 over 5 factorial. And that's good enough. Now, if you wanted to, you could go a little bit further. This is the same as 1 over 6 plus 1 over 120, which becomes 21 over 120, because you multiply here by 20 over 20. And of course, 21 and 120 have a common factor of 3, and so you could say 7 over 40. But 1 over 3 factorial plus 1 over 5 factorial makes it more clear about what's going on. If we're trying to obfuscate and say, ha ha ha, where did this number come from? We'd write 7 over 40. But why would we obfuscate? What? That's not our goal. Our goal is to illuminate, to understand things even better. That's what we want. Always to understand things better. Our next problem. Find the sum from 1 to infinity, cosine squared pi over n minus cosine squared pi over n plus 1. Wow, beautiful. Beautiful sum. Now, this came from an old final exam, and it was a problem that a lot of people did really bad on. And you're like, what? That doesn't seem so bad. Let's dig into it. Okay. Now, first off, is it geometric or telescoping? It's got to be telescoping, right? It can't be geometric. It's not something to the nth power. But really, look what it's saying. See here, you only see an n versus an n plus 1. So these are offset by 1. So it says, oh, great. So what that means is, if I write down terms, I'll get cancellation. All right. So what happens? Well, what happens is, let's write down the first couple of terms. All right, so you get cosine squared pi over 1 minus cosine squared of pi over 2. That's terrible looking cosine squared pi over 2, but that's all right. Plus cosine squared pi over 2 minus cosine squared pi over 3. And plus cosine squared of pi over 3 minus cosine squared pi over 4, and so forth. Now, our inclination is, ooh, great, our offset is by 1, and then we look and we say, we're getting cancellation, cancellation, dot, 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 dot. It must be, that's our answer, so it's 1. Because cosine of pi is minus 1, you square that, you get plus 1. So, is that our answer? And why not? Okay, you have to be careful. Now, it's so often the case in telescoping that you only have to pay attention to the start that we also forget you got to kind of pay attention to the end. What's happening way down in the tail? Because when you talk about telescoping, well, it means that you're going to be left with one term at the start, and then in a partial sum, there's a term at the end. Put a different way, you have to ask the question, what's happening to this piece? As n goes to infinity, what do we see? Well, it's going to cosine squared of 0. So it's really, it approaches 1. When it just approaches 0, that says, look, don't worry about the end, and life is good, and you're done. When it approaches a different number, it says, oops, pay attention to the end as well. So, because it's approaching 1, let's be careful. Here's how you're careful. You think about what a series is. It says, look, we can't do infinitely many terms, so we'll do finitely many terms. So you do a sum from 1 up to some point of cosine squared of pi over n minus cosine squared of pi over n plus 1. You say, look, no worries. You write it out, same as before, except it doesn't go dot, dot, dot forever. It stops at some point. And you say, look, everything canceled except the very first term. So you say it's going to be cosine squared of pi and minus the very last term. So for example, maybe it would be this cosine squared of pi over 4. It just depends. But it would turn out to be, in general, cosine squared of pi over capital N plus 1. And now we say, okay, well look, what's this doing? As we let capital N go to infinity, what do we see? Well, we see that this goes to, the first term is still 1, but the second term is also 1. So it goes to 1 minus 1. And therefore, our answer is 0. The limit is 0. It all cancels out. Yeah. That's it. That's it. Wow. Wow. Cool. Amazing. And yeah, students didn't like this one. I don't blame them because it's easy to forget. Oh, got to pay attention to what's happening at the end of a telescoping sum. If it's not going to zero, something happens. And this is that kind of rare case where it's like, oh yeah, we did have to pay attention because something did happen. So, but now that we know, you can't fool us twice. Fool us once, shame on you. Fool us twice, it's not nice to fool people. Okay. So our next problem. Suppose that we have this sequence. Well, here's the first few terms. It's 1 over 1, 3 over 1, 3 over 4, 9 over 4, 9 over 16, 27 over 16, ... Well, it says, how do you form it? You start with 1, and then you alternate between multiplying by 3 or by a 4. So in other words, you see, you multiply by 3, then by a 4th, then by 3, then by a 4th, then by 3, then by a 4th, and so forth and so on. All right, so what can we do? Now, we can probably quickly tell what kind of technique we're using. First off, we know that we're supposed to find. There's not a lot of things we can do, so we're probably thinking, okay, geometric or telescoping. But there's a key word here. The fact that we see multiplying showing up. See, multiplying is just a very fancy way of saying geometric. So when we see, oh, there's this process that comes along that involves multiplication, that really says, okay, there's some geometric thing going on here. Now, is this sequence of numbers that we have right now geometric? And why not? It's not geometric because to be geometric, you always have to multiply by a consistent amount. The fact that we say, oh, sometimes we multiply by 3, but other times we multiply by a 4th, it ruins our consistency, which means we ruin it being geometric. So it's not geometric right now. So we have to think about, okay, first off, you said not geometric right now. What can we do? The fact that we alternate is kind of a big clue. So alternating means sort of like we're going between two states, right? This, then that, then this, then that. We're going back and forth, ticka-taka, ticka-taka. Okay, well, let's use that to our advantage. So what we should think of saying, all right, let's think about taking our sequence of numbers here, and we have to add them up, but let's split them. In other words, let's think about taking them in every other term, because that's sort of the idea of alternating, right? So let's start with the first term, and suppose we just look at that. So we'd have 1 over 1, then 3 over 4, and then we skip, then 9 over 16, and then we skip again, 27 over 64, and then so forth and so on. Now, what do you see here? See, because we skipped 2 steps, there was a multiply by 3 and a multiply by 4 that happened. So the effect is multiplied by 3/4. Again, skip 2 steps. Since we did both a 3 and a 4th, that's the same as multiplied by 3/4. And again by 3/4, and so forth and so on. So in other words, if we start with the first term and take every other, that's geometric. Well, what if we started with the second term and took every other? Well, that would be what? 3 over 1, 9 over 4, 27 over 16, 81 over 64, and so forth. And again, what do we see? Between 2 consecutive, there was multiplied by 3 and divided by 4. So 3/4, 3/4, 3/4. So, in essence, what we can think of doing is that we're taking our list of numbers here and we're pulling them apart. And we're saying, okay, this original list doesn't behave like geometric properly, but when we separate every other one and every other one, it is behaving like a geometric. So we have tools. So we say, aha, cool. So what we'll do is we'll do this by adding up two smaller sums and putting them together. So let's think about it. So what's our first series? Well, we really have 1 over 1 plus 3 over 4 plus 9 over 16, so forth and so on. And then after we finish adding those, we'll add 3 over 1 plus 9 over 4 plus 27 over 16 plus 81 over 64, and so forth. And now we say, okay, great. What's the first term? Well, here it's 1. And in here, the first term is 3. Now, the reason I'm emphasizing it is to do geometric, you need to know the first term and your ratio r. What are you multiplying by? Well, here, 3/4. Here, still 3/4. So now we're like, perfect. Our ratio is less than 1. We have nice geometric series. So the first sum will become 1 over, then downstairs, 1 minus 3/4. The second one, first term is 3 over 1 minus 3/4. Well, the good news, 1 minus 3/4 is pretty easy. It's a fourth. And if you flip a fourth, it becomes multiplied by 4. So what do you really have? Well, you have 4 from the first term, and 3 plus 3 times 4, which is 12 from the second, giving us 16. And that's it. That's our sum. Wow, nice, cool. Ah, that was fun. The idea of pulling things apart, really separating, looking for the geometric pattern that was there. Ah, what a nice problem. Good problem. Good, fun problem. All right. Well, time for our next problem. Find the sum, n equals 2 to infinity, 6 over 4n squared minus 9. Now, definitely it's not geometric. We can see that for sure because it doesn't have n up in an exponent. So it's not geometric. Forget that. That leaves us with telescoping. And it doesn't look like telescoping yet. That's okay. It might someday. You might say, oh, there's a minus sign, right? So we can break it up. The minus is downstairs. If the minus was upstairs, oh, sure, we could break it up then. Minus downstairs. No. That's not how subtraction works in the denominator. When you see subtraction downstairs, it usually means more work. More work. Now, what is the more work? Well, the idea is to say, hey, we're doing a sum. If this had been an integral, we would say, let's do some kind of like partial fractions. So since it's a sum, let's do some kind of partial fractions and see what we get. Now, the nice thing is 4n squared minus 9, that's not just any number. It actually, or rather should say any polynomial, it factors really nicely. See, you can think of it as 2n quantity squared minus 3 quantity squared, which means it's a difference of squares. All right, well, that says we can write it as 6 over 2n minus 3 and 6 over 2n plus 3. All right, well, good, right? Because it's a minus b, a plus b. I really should have said there's an intermediate step. 6 over 2n minus 3 times 2n plus 3. And there's no 6 there. It's got ahead of myself. So it factors as a over 2n minus 3 and b over 2n plus 3. There we go. There we go. We don't know a and b yet. We'll find that out in a second. Clear our denominators. Okay, so we're going to get 6 is equal to a times 2n plus 3 plus b times 2n minus 3. And now we can choose nice values for n. And don't worry if you're like, oh, shouldn't we choose like nice whole numbers? No. Any value you want. And so we pick numbers that make these terms, well, simple, right? And oftentimes the way to make things simple is make something a 0. So we could choose, say, n equals 3/2. Why? Well, 2 times 3 halves would be 3. Subtract 3 is 0. That knocks that term away. And we come to the conclusion 6 equals a times 6. Or a equals 1. If we chose negative 3 halves, 2 times negative 3 halves is negative 3. Plus 3, 0. That term gets knocked out. So 6 equals minus 3 is minus 6 times b. So minus b 6, or b equals minus 1. So what that tells us is that this sum really looks like the sum from 2 to infinity of a over 2n minus 3, which would be 1 over 2n minus 3, then plus b, which would make it minus 1, so minus 1 over 2n plus 3. Okay, there we go. Now it feels more like telescoping because we expect to see a subtraction and that the terms should look very similar to each other. So let's take a look and see what we have. We'll start by writing down the first couple of terms. So when n equals 2, this would be 1 over 4 minus 3, that's 1 over 1. Here, 4 plus 3, 1 over 7. Add, when n equals 3, 6 minus 3 is 3. And then here, 6 plus 3 is 9. When n equals 3, well, excuse me, we did already n equals 3. N equals 4 is the next one, which would be, it'd be 8 minus 3, making it a 5. And then subtract, here, 8 plus 3 would be an 11. Okay. You look at this, oh, hopeless, hopeless. Nothing's happening. What? But wait, hold on, keep going. Next term would be what? Well, it would be n equals 5. 10 minus 3, 7. And then we're going to end up here, subtract 10 plus 3, 13. Okay, now we're feeling better. And you'll see next term would be 1 over 9, 1 over 15. And the next term would be 1 over 11, and 1 over 17, and so forth. Now, we say, wow, it took a while, but we didn't get some common terms, right? The 1 over 7 from the first, after 1, 2, 3, canceled. The 1 over 9, canceled. The 1 over 11, canceled. And that should continue. Now, why did it take 3? Well, we could say it comes back to where we had our pieces, right? So if we think of this as our basic mold, 1 over 2n minus 3, we can say, all right, so I want to write this as 1 over 2 times something minus 3. Because this will help me figure out the right offset. You know, how far off do I have to go to get my cancellation? So I say, okay, I'll need an n, because I need to end up with 2n. And I need to have it so 2 times something minus 3 gives me 3 again. Well, if we make it plus 3, 2 times 3 is 6, minus 3 is 3. The fact that it's n plus 3 versus n says when you go down 3 terms, that's where you see your cancellation. So that's how I knew that, yeah, if we don't only stop and said, nothing's happening, and given up, we would have said we would have missed out. It's 3, steps away. That's where we see our offset. Now, the other thing is what's happening to the pieces at the end. And so you look at this expression, this is enough to say, hey, this goes to 0. So what's going to happen is that as we go along, you have 3 terms left at the start, you'll have 3 terms at the end, but notice that these 3 terms at the end, as we go further and further down, what's happening? They're getting smaller. They go away. They go to 0. So, what's our conclusion? Our conclusion is, we're going to end up with only these terms left at the process when we go all the way to the end. So we get 1 over 1 plus 1 over 3 plus 1 over 5. Well, all right, common denominator would be 15. So we'll get 15 plus 5 plus 3 all over 15, because we have to multiply by 15, by 5, and by 3, which gives us a final answer of 23/15. That's it. We're done. Woohoo! Nice. Nice. Good stuff. Wonderful. All right. Well, let's keep going and see what we can get. Okay. So, our next problem. Oh my gosh, wow. All right, well, find the sum from 1 to infinity of 3 over n plus 3 times square root of n plus n times square root of n plus 3. Oh my gosh, okay. Well, okay, we know for sure it's not geometric, so that's good. Good news for us. But how are we going to approach this? Oh, wow. Wow, that's so crazy. Now, looking at this, we say if we are going to have to find it, and we do because it says the word find, we say, all right, well, pretty much the only tool left in our tool chest is if this is some kind of telescoping in disguise. In other words, perhaps somebody came and did some obfuscation, and we just have to unobfuscate. Okay, so, let's think about what we could do. Let's get rid of our square roots in the denominator. Now, how could we do that? If you have square roots downstairs in the denominator, what could we possibly use to get rid of them? We could conjugate. See, conjugation, it's a great way to help us get rid of square roots, and we have square roots. So, our first step is we're really going to be doing a lot of just rewriting our summand, the piece that we're adding up. So we're rewriting our term that we're adding with the expectation that when we do rewrite it, it'll become easier to add. It seems like a reasonable plan. Okay, so we're going to multiply by the conjugate, and here it just says we're going to change that sign in the middle. So we'll have n plus 3 times square root of n minus n times square root of n plus 3. And we're going to multiply both top and bottom. Now, notice that in addition to getting rid of the square roots, there's something else kind of cool which is going to happen here, which is we're going to get a minus sign because we really like having something subtracted when we talk about doing telescoping, because the goal is to get some cancellation with some terms that happen later on. So the fact that we're getting a minus upstairs is a bonus. It's making us feel like, yeah, we're on the right track. We're doing what we should be doing. Okay, so this will be the sum from 1 to infinity of what? Again, we haven't done any summation. We're just working on simplifying. Well, we haven't done much with the upstairs yet. We won't worry about that yet. So there's 3 times that whole expression. Okay, it is what it is. We'll come back to it. Over. Now, when you multiply by the conjugate, it's a plus b times a minus b becomes a squared minus b squared. So that will become a squared n plus 3 squared times n. Okay, that's we'll get when we multiply the first terms. And then minus, now here, what will we have? We'll have n squared times n plus 3. Okay? All right. That's something. Now, let's look at the denominator for a second. If we wanted to simplify, what could we do? Well, they have some common terms. So we could factor out an n plus 3 and an n, because that's common. And then we'll be left, well, there's n plus 3 from the first term, and there's an n from the second term. That's being subtracted. And, ooh, the n's cancel. Oh, there's a 3 there. There was a 3 there. Those will cancel. So that's why there was a 3. They did it in anticipation. Cool. All right. So where are we at? Well, we now have this expression n plus 3 root n minus n over root n plus 3 all over n plus 3 times n. Now for telescoping, we really like to say something minus something. So we're going to split it into two pieces. So this is going to be the sum from 1 to infinity of, well, n plus 3 times root n over n plus 3 times n, and then minus n times square root of n plus 3 over n times n plus 3. All right, so n plus 3 times n. Here it's the same thing, just written in different order. And now we're like, wow, the simplification continues. It's almost like they were expecting us to do lots of crazy, simple stuff. Cool. And it gets even better, right? Because what do you see? Square root of n over n. Well, that is another way of saying 1 over square root of n. And here, square root of n plus 3 over n plus 3 is 1 over square root of n plus 3. And now we're like, that is definitely telescoping. And in fact, not only is it telescoping, we can see that here, this is offset by 3. Because we see it's this n versus n plus 3. So when we look at our terms, if we go 3 down, that's where we're going to get cancellation. And the other thing, of course, is that these terms are going to 0 as n goes to infinity, which means that it's going to be 3 terms at the start because of our offset by 3, and then 3 terms that are left over in the partial sum, but the 3 terms go to 0. So we're now ready to pretty much see what happens, right? We can say, look, this is 1 over square root of 1 minus 1 over square root of 4. And we'll write down a couple of terms just to emphasize, hey, yeah, our intuition was right. 1 over square root of 2 minus 1 over square root of 5. 1 over square root of 3 minus 1 over square root of 6. 1 over square root of 4 minus 1 over square root of 7. 1 over square root of 5 minus 1 over square root of 8. 1 over square root of 6 minus 1 over square root of 9, and, so forth and so on. And what we're going to see, the claim offset by 3, right? So let's see. Is that true? Well, okay, so here's 1 over root 4, 1, 2, 3. Yep. 1 over root 5, 1, 2, 3. 1 over root 6, yep. And it keeps going. Da, 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 da. So what will be left? Well, the answer, the things that will be left, are the things at the start that don't cancel. And so we have 1 plus 1 over root 2 plus 1 over root 3. And there we go. That's it. That's our answer. Now we could write that in various ways. One way you could write it, if you wanted to obfuscate a little bit more, is you could say, oh, if you multiply, get a common denominator of root 6, you can say this is root 6 plus root 3 plus root 2 all over root 6. And then people will be really confused, like, whoa, where did that come from? Of course, when you write it like this, it's like, oh, I see what happened. Yeah, it's just the first 3 terms that aren't canceling out. Cool. So, all right, good. Whew, this one's fun because you get to do algebra. Oh, man, algebra. What a wonderful, beautiful thing. We love you, algebra. We love you. Okay, well, let's take a look at the next one. Find the sum from 1 to infinity of 1 over e plus 1 to the n times e to the n. It's trying to look like it might be partial fractions, but what do we notice? Where does the n show up? You see, it's not down here, it's up in the exponent. When we see n in the exponent, we should think, hey, could this be geometric? And we see, oh, actually, this is, a way to rewrite it is the following, as 1 over, and I can just write as e plus 1 times e, all raised to the nth power. So that's part A. And then we say, well, this is really nice. It's a number. It's a weird-looking number. I grant you that. But it is a number. So, according to the rules for geometric sums, it will be the first term, which corresponds to n equals 1. So 1 over e plus 1 times e. This is sometimes we call this a in our formula. It's just the first term. Divide by 1 minus the ratio you multiply by. And here, it's this expression. So 1 over e plus 1 times e. Now, that's the correct answer. Let's multiply top and bottom by e plus 1 over e. If we do that, well, we'll get 1 there. Then we're going to get e plus 1 times e minus 1. So this can be written as 1 over e squared plus e minus 1. And we're done. That's it. So this one was if you see that it's geometric, no problems. If you think, ooh, maybe it's partial fractions, you'll have some problems because it's not going to work out. Okay, so for part B, well, okay, now we have to find that sum. This one is definitely not geometric because it's not n in the exponent. So, all right, so it's got to be something else, and because we're asked to find it, well, it could be telescoping. That's usually the only two options, right? Or, well, there's another option, but we'll save that for another day. Okay, log of 1 plus 1 over n. Well, notice we can rewrite that as n plus 1 over n over log of n plus 1. Yes? Okay, so this is our sum, 3 to infinity. Now, log of n plus 1 over n. Why did we do that? Well, see, the original is a 1 plus 1 over. Logs are not great with addition. They're actually pretty lousy with it. But they're wonderful with things like multiplication and division. So by rewriting it in a form like division, it makes it so we can actually make progress. In particular, it says, hey, I can rewrite the top as a subtraction. Log of n plus 1 minus log of n. Divide by log of n times log of n plus 1. And now, let's pull it apart into two terms. Because when we think telescoping, it's something minus something that's been offset. So this will be the sum from 3 to infinity. And the first will have log of n plus 1 divide by log of n plus 1 times log of n, which will become just log of n. The second term, log of n over log of n times log of n plus 1, the log of n cancels, so minus 1 over log of n plus 1. And now we're like, perfect, exactly what we want. It looks like a telescoping sum because it is telescoping. They're the same form. This is offset by one term. So what happens? Well, we're going to get 1 over log of 3 minus 1 over log 4. And then in the very next term, when n equals 4, 1 over log 4 minus 1 over log 5. And in the next term, 1 over log 5 minus 1 over log 6, and so forth and so on. Now, because it's an offset by 1, we only need to go 1 away to cancel. Do we need to worry about what happens at the end? Well, the question we ask ourselves, what happens to 1 over log n as n goes to infinity? That tells us what do we need to worry about. Do we need to pay attention? And do we need to worry about something kind of devious happening? Well, as n goes to infinity, log gets big. Takes its time, but it gets there. So 1 over log goes to 0, which means that the terms on the end, and I should have said there's a dot, dot, dot that I forgot to write down, these terms on the end are going to be shrinking as we go along. So the only term that's going to be left when we look at the limit of the partial sums is this first term. And so our final answer becomes 1 over natural log of 3. And that's it. That's it. We're done. Wow. Cool. What a beautiful problem. Beautiful problem. All right. Great. Well, more problems to do, right? Oh, yeah. Sure, of course. Always more to do. Well, let's look at our next one. Find the sum from 2 to infinity of 2 over n cubed minus n. Now, we say, okay, not geometric, so we're thinking telescoping. We're like, oh, we've seen some of these before. It's just like partial fractions, right? And then we'll have telescoping and life is good. Okay, great. So we put on our sort of partial fractions cap. We say, all right, well, let's see, what do we have? 2 over n cubed minus n. Well, you can factor out an n. Term, and it knocks out the middle term, which means we just have the last term. So minus 1 times minus 2 tells us that 2 is equal to 2c. Yes? Right? Minus 1, minus 1, minus 1. Or, what do we have? C equals 1. All right, so now we know A, B, and C. And so we can rewrite that in the following way. This becomes the sum, n equals 2 to infinity. And let's put the denominators from largest to smallest. So notice we really should have swapped that. So it should be BAC. All right, so it's going to be 1 over n minus 1. And then minus 2 over n, and then plus 1 over n plus 1. All right, there we go. Is this telescoping? That's a good question. Why does it not feel like telescoping, right? Well, because you don't have something minus something. It's kind of like, oh, you have two things being added. one thing in the middle being subtracted. What does that mean? Okay, so let's think about what that really means. Let's look at the first couple of terms and think about what's going on. And we'll look at some other ways we could have seen it once we get to the end. Okay, so what do we have? Well, we can say this is 1 over 1 minus 2 over 2 plus 1 over 3. So that's, we're plugging in n equals 2. And then plus, plug in n equals 3. It'll be 1 over 2 minus 2 over 3 plus 1 over 4. All right, plug in n equals 4. And 1 over 3 minus 2 over 4 plus 1 over 5. All right, n equals 5. 1 over 4 minus 2 over 5 plus 1 over 6. All right, maybe one more should be enough for us to hopefully spot what the pattern is. Okay, so, and so forth. So, what's happening here? Well, let's look in and see what we can see. Let's start by notice this minus 2 over 3. It can combine with the 1 over 3 in the previous sum and the minus 1 over 3 in the next sum. So if we put them all together, we'll get 0. Okay, well, how about this minus 2 over 4? Well, I can combine it with the previous 1 over 4 and the next 1 over 4. They'll all cancel. The 2 over 5, well, okay, I can combine it with the previous 1 over 5 and the next 1 over 5, and they'll all cancel. So what's happening is we're getting cancellation, but we have to be careful as far as what's actually getting canceled. We have to combine pieces together in sort of a variety of ways. So what doesn't get canceled? That's the key. Well, what doesn't get canceled is the first couple of terms. So, namely, those terms at the beginning don't get canceled, plus there'll be a couple terms at the end. So there's 3 terms at the start, 3 terms at the end. All right, well, that's not so bad. What's happening to these 3 terms on the end? Well, notice what's happening to these pieces. They're going to 0, so we don't need to worry about them. So what's left? Well, we have 1 over 1, which is 1, minus 2 over 2, which is 1. So 1 minus 1 is 0. And then there's a half, which means we're left with 1/2. And that's the answer. So, in other words, this does telescope, but not just a matter of simple like, oh, this term will cancel with exactly another term a couple down. But rather it's like, okay, this term, because there's 3 pieces, right? The middle piece will cancel with the last piece from the previous term and the first piece from the next term. But again, the same idea of there's this collapsing going on, and so we can say, oh yeah, there's still telescoping. We could have looked at it in a slightly different way, which is to say the following. This sum here, I could have said, oh, it's like 1 over n minus 1 minus 1 over n, right? And then minus 1 over n plus 1 over n plus 1. See, we just said, oh, split that minus 2 over n into parts. And then you could say, oh, hey, go even further. If we combine and make this into a minus there, so that's now become a really thick minus sign, what do we end up seeing? Oh, it's like this piece is telescoping and that piece is telescoping. And so we say, okay, just do both of them individually. They telescope, and then when you're done, what's left? And that'll be the answer. So that's something else that we could have done. But I'm satisfied with what we got. A half. That's kind of a nice answer. It's really kind of pretty, because you look at that expression, 2 over n cubed minus n, it doesn't look like the easiest thing to add, but yet wow, it's a half. Simple, elegant. On the other hand, suppose you ask the question, what if it was just 2 over n cubed? Can you do that? No, hopeless, hopeless. We know it to high precision, but the thing is we don't know if there's a nice way to express the answer, which is amazing because 2 over n squared, yeah, no problem. 2 over n to the fourth, no problem. 2 over n cubed, sorry, can't help you. Well, that's a different story. All right, well, keep going, right? Oh, yeah, sure. Lots of problems left to do. Find the exact value of the sum, n equals 0 to infinity, and we're integrating from 0 to 2 of 1 over 1 plus x plus n squared dx. Okay. Well, this should be interesting. What can we do? Well, we should think about how to approach this problem. Now, there's a couple things that we could do. And, okay, let's talk about things that we could do. One of the things that we could do is we could say, well, let's put all the integrals together and see what they become. And then when we're done, maybe we can say, it's like one big infinite integral, and we'll just do that integral. Another thing we could do is we could actually just integrate it, right? And I think let's try that. Because what is it? See, it's 1 over 1 plus, you see this x plus n squared dx. Well, what's the integral of 1 over 1 plus u squared du? Right? Because the plus n doesn't really do anything. It's just a shift. If you covered up the plus n, you say, whoa, our favorite integral. You're back. It's the arctangent. So we could say, hey, this is our sum from 0 to infinity of arctangent of x plus n evaluated from 0 to 2. And remember, because you might say, wait, which one gets plugged in? Are we plugging in for x or plugging in for n? X is the variable. So it's really, like x equals 0 to x equals 2. So in case you're forgetting, just remember, it's x equals 0 to x equals 2. So we say, so this is like the sum, n equals 0 to infinity of what? Well, it's going to be arctangent of n plus 2 subtract arctangent of n. All right, great. Now, where to go from here? Well, it looks telescoping because it is, right? We say, hey, there's this subtraction going on. Good stuff. When we see subtraction, that's a sign that says, we could actually combine these together and get cancellation. Okay, so let's see what happens here. So, what do we see? Well, it becomes arctangent of 2 minus arctangent of 0. All right. And then plus arctangent of 3 minus arctangent of 1. Okay. Plus arctangent of 4 minus arctangent of 2, and so forth and so on. Because of the n plus 2, we say, we should look 2 steps down to look for cancellation. And we say, notice the arctangent of 2 would cancel with the arctangent of 2. And if you look at this arctangent of 3, it would cancel with the next term. And you see, cancellation. And you're like, wow, cool, beautiful. So, does that mean everything cancels except this arctangent of 0? Well, okay, it wouldn't just be arctangent of 0. We would say these two terms aren't canceling because you have to look at the first term 2 terms down. So the arctangent of 4 would cancel. And so it looks like, what is arctangent of 0? Well, 0. Arctangent of 1 is pi fourths. So this is negative pi fourths. Okay. Why should we be very suspicious of this answer? Not only because I'm using a very high-pitched voice. No, there's something wrong with this answer. It is wrong because, look, this function we're integrating is not negative. It's always positive. So we're adding up positive pieces and we're getting a negative result. What's happening here? Well, what's happening is if you only pay attention to the first terms in a telescoping sum, you miss if there's something going on with the last terms in a telescoping sum. And in this case, if you look at the arctangent, what you see is you say, oh, this does not go to 0. Where does it go to? It goes to pi over 2. So the terms on the end aren't going away. They're actually going to a value. So we've got to account for that. So that's why the answer is not negative pi fourths. All right, so what do we do? So, and especially because we're running out of space, right? So it can't be something very fancy. But we do have this right notion. It is telescoping. We have an offset of 2, which means that things which are 2 apart will get cancellation. So when we think about the telescoping sum, a partial sum will have 2 terms from the start and 2 from the end. So what we really can say is, hey, our sum from 0 up to some ending point n of this expression arctangent of n plus 2 minus arctangent of n will have the 2 terms at the start that we already mentioned. So that's minus arctangent of 0 and minus arctangent of 1. And then plus the 2 terms at the end that don't cancel. Arctangent of capital N plus 1 and plus arctangent of capital N plus 2. So those are the pieces that are left after we collapse our sum. Remember, the telescoping idea is we collapse down. And now we look and say, all right, let's just think about every piece. Okay, we know arctangent of 0 is 0. Arctangent of 1 is pi over 4. And then as n goes to infinity, we go to the asymptote, which is pi over 2. And so both these last pieces go to pi over 2. So what we end up with is minus 0 minus pi over 4 plus pi over 2 plus pi over 2. And if you put it all together, you can think of it as pi minus pi over 4, giving us a grand total of 3 pi over 4. And that's it. We're done. Woohoo! Nice! Cool! All right, fun problem. Fun problem. I was really trying to hide this telescoping series with arctangent by using integration to hide the arctangent. That was good. Nice trick they did. But we got through it. All right. Find the sum, 1 to infinity, of L divided by L plus 1 factorial. And it says, hint, add 0. And you're probably like, what? Okay, so we know it's not geometric because this index, in this case it's the letter L, it can be any symbol we want. It's not showing up in the exponent. That's where geometric would need to have that. So we're trying to look for something that's telescoping, but for telescoping we really need to have like 2 terms, something minus something. We don't have that. Not yet. And so there's a hint, add 0. Now there's lots of ways to add 0. You could literally add 0. But when something says add 0, it doesn't mean add the value 0. What it really means is add something which is equal to 0, but whose terms can be somehow conveniently used to simplify expressions. Now, in our case, we say, okay, well, I have an L upstairs, and then I see this L plus 1 factorial downstairs. And for that, we say, oh, L is not so off from L plus 1. plus 1 off, right? So what we could do is we could say, hey, we can write this as the sum 1 to infinity L plus 1 minus 1. See, that's plus 1 minus 1. That's our 0. Now, why do it? Well, because by doing it, we make these pieces compatible. That's why we do things like add 0, multiply by 1, so that our terms are more like. See, once terms are like, then we can do some kind of cancellation. When they're not like, we can't get cancellation going. All right, so this becomes the sum from 1 to infinity of L plus 1 over L plus 1 factorial, subtract 1 over L plus 1 factorial. Now, not a lot you can do with this second term. Can we simplify the first term? Now, you might say, oh, can't we just cancel off the L plus 1s? Isn't it just going to be 1 over 1 factorial? No, no, that's not how it works. No, okay, it's not that. But what is it? Let's be careful here. So remember, what do you have? So you have an L plus 1, and L plus 1 factorial means you start at L plus 1 and you keep multiplying. L plus 1, L minus 1, until you get down to 1. So L plus 1 factorial would be L plus 1 times L minus 1, all the way down to 1. But really what you can think of, if I have an L plus 1 factorial, I can say I'm going to pull off the first term. So I'm going to pull off 1 L plus 1, and I say, all right, what's left? Well, what's left is everything else, which, L minus 1, 3, 2, 1. So what's left is the factorial, starting at L. Now the L plus 1s cancel, so it becomes 1 over L factorial. And we're like, whoa, that's really good for us, because now this says, hey, this is the sum, starting at 1 to infinity, of 1 over L factorial minus 1 over L plus 1 factorial. What? So you get 1 over 1 factorial minus 1 over 2 factorial plus, and notice our offset is just 1, so 1 over 2 factorial, perfect, and 1 over 3 factorial, and then the next term will be 1 over 3 factorial minus 1 over 4 factorial, and so forth, and so on. Whoops. If I could get these numbers right. So what's going to end up happening is we're going to get a lot of cancellation, and we have to think about what's left. Well, what do we mean by lots of cancellation? Offset of 1, cancel, 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 and what's left? You have the term at the start, and then you have that sort of trailing term on the end. What is that term on the end going to do? Well, this goes to 0, because your factorial gets huge as you head off to infinity. So the only thing left is the term at the start, and therefore our answer is 1 over 1 factorial, also known as 1. And we're done. Cool. Good. Wow. Nice. That was a fun problem. Haha. Add 0. What a good thing. Whoever came up with adding 0, they were pretty good. They knew what they were doing. They had a plan. All right. So, next problem. Find the value, or possibly values, of b so that when we sum from 0 to infinity of 1 plus b to the power n divided by 1 plus b to the power n, we get 5. Now you might say, wait, you said the same thing on top and bottom. You're right, except I didn't talk about parentheses. So the difference between the top and bottom is there's parentheses added. Does that matter? Oh, it matters a lot. Yeah, by adding the parentheses, you see here in the exponent, it's only b raised to the power n, but downstairs It's 1 plus b raised to the power n. So be careful. Exponents, well, parentheses matter. Parentheses matter. And they're wonderful tools. I strongly encourage you to use them as much as possible and to respect them when they're already being used. Well, let's get to work. So we know what we want the result to be. We just have to figure out what the correct value for our choice for b should be. So, okay, we say, hey, let's rewrite our sum in a more convenient way. Our mindset is geometric. The reason our mindset is geometric is we see an exponent to the nth power. Exponent to the n, we think geometric. So we can say, hey, this is the sum from 0 to infinity of, split into two pieces, 1 over 1 plus b to the n, and then b to the n over 1 plus b to the n. So I'm using the fact that I have addition in the numerator. That lets me break things up. So we'll say this is the sum 0 to infinity of 1 over 1 plus b, and actually we'll just raise that to the whole power n, plus the sum n equals 0 to infinity of b over 1 plus b raised to the power n. So I did two things. One of them was easily justified. The other one, I'm kind of cheating here. Shh, don't tell anybody. The easy to justify is, oh, if I have two things raised to the nth power, I can just write it as one thing to the power n. Where's my cheat? Well, the cheat is, how do I know I'm justified in splitting the sum? The answer will come at the end. Essentially, what we're going to do is we're going to say, hey, these numbers are going to be such that each of these is converging, and therefore, because the individual pieces converge, I'm allowed to split. So that's what we're going to say. In fact, well, let's wait till we get there. Okay. So now we're like, hey, let's find these sums. The first term to the 0th power will always be 1. Anything to the 0th power we can take as 1. So we're going to get 1 over, see our ratio is what's inside the parenthesis, 1 minus 1 over 1 plus b. Plus, again, 0th power is 1 over 1 minus b over 1 plus b. All right, well, let's multiply top and bottom by 1 plus b in both cases, just to help us get rid of our fractions within fractions. So we have 1 plus b over 1 plus b minus 1 plus 1 plus b over 1 plus b minus b. Okay, the b minus b cancels, same way as the 1 minus 1 cancels. So that's good news for us. It's great news for us, really. So what do we have? Well, okay, this is, if we go ahead, we can say, look, 1 over b plus b over b, which is 1, plus another 1, so plus 2, plus b. So if this sum equals 5, then it has to be the case that 1 over b plus 2 plus b has to equal 5. And now we're like, wow, this looks like an algebra problem. There's no more infinite series. We just have to figure out what b makes this true. So we'll multiply through here by b. All right, that would become 1 plus 2b, right? 2 times b is 2b, plus b times b, that's b squared, equals 5b. Or we could say b squared, subtract across, minus 3b, and then plus 1 equals 0. And now we're like, hey, does it factor? No! Okay, not everything factors. We've been spoiled working on some of these problems because so often they have factored. Well, all right, even if it doesn't factor, what do we get? Well, we get b equals, you take the minus the coefficient in the middle term, So that would be minus minus 3, that's 3, plus or minus the square root. Now you square that, 9, then minus 4 times 1 times 1, so 9 minus 4 all over 2. So you get 3 plus or minus square root of 5 over 2. All right, good. And then that's those are the candidates. Now, here is where we're going to sort of say, and those are the correct answers. But at this point, there is a technicality that you have to check. So I will tell you that both of these work. So it turns out that there's 2 possible choices for B. Do you see the technicality? Well, the technicality is, how did we know that these were the sums over here? How do we know that that's true? So what we need to do is we have to say, and on a side note, these are both positive numbers. It has to be that 1 over 1 plus b is less than 1, and we need to have b over 1 plus b be less than 1. Okay, so how do you check these? Well, the good news is, as long as you're a positive number, b over 1 plus b is definitely less than 1, right? Because it's a positive number divided by a larger positive number. And so if you have a small number divided by a larger number, it's below 1. These are both positive numbers. Root 5 is below 3. So 3 minus root 5 is positive. So this inequality is pretty easy to check. Well, how about this inequality? What needs to be true? Well, since 1 plus b is positive, that'll be true if 1 is less than 1 plus b. Okay, well, you can cancel the 1s, which is true as long as b is positive. Okay, well, they are both positive. Oh, that was actually easier to check than I thought. Okay, good. So the good news is they both work. All right. Phew, I thought it'd be tricky. Wonderful. So they are both solutions. So there are 2 values that make it true. And this is a case where you probably would not have guessed. Oftentimes people say, oh, I could have just guessed it. Why can't I just guess? No, guessing has limitations. 3 plus or minus root 5 over 2, you wouldn't guess that. So, cool. All right, well, keep going, right? More problems to do. Okay, on to our next problem. So, here we go. Express 0.16616616616 as a geometric series and find the sum of the series to write the number as a fraction. And in particular, what we're about to do is something which can be generalized to show any what we call repeating decimal. So any place where you have a decimal expansion, and it just says, oh, this is, after a certain point, it says this, copies to that, and so forth and so on, all the way forever. Always can be written as a fraction, and this technique shows how to do it. Okay, so what to do? Well, so we have to express this as a geometric series. So let's think about how that can be done. What we should do, when we're thinking geometric series, we want to get something where, to get from one step to the next, we always multiply by a consistent amount. And so when we see that, it sort of like says you're doing the same thing at every stage. So here we could say, oh, it's almost like we're just taking this block of 166 and we're copying it over and over and over again. So if we could somehow have a geometric series that captures that behavior, that could be the one we're looking for. So let's think of this as really 0.166 plus 0.000166 plus 0.000000166 plus 0.000166 0, 0, 0, 0, 0, 0, 1, 6, 6, and so forth, right? Well, what's going on here? Well, at every stage, you're like moving the dot 3 places. If you think of the first number, it's 166 over 1,000, right? Because you have 166, and then you move the dot 3 places over, dot, dot, dot. Okay, the next number, well, we have the same 166, but now, instead of moving the dot 3 places, we moved it 6 places. So that means we factored by another 1,000. And here, it's again 166, but now it's by how many places? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now that's like 1,000 cubed. And 166, and then, okay, how many places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1,000 to the fourth, and so on. So in particular, what we have, this will become the sum where we start from 1 to infinity of 166 over 1,000 to the n. So there's our geometric sum. Okay, great. But what is the sum? Well, now we can find it. In fact, we can see in this form, what do we see? The first number. So 166 over 1,000. All over 1 minus, what are we multiplying by at every stage? Well, we're multiplying by 1,000 downstairs, which really means we're multiplying by 1 over 1,000. And all right, great. Well, let's multiply top and bottom by 1,000. So we end up with 166 over, well, 1,000 minus 1 is 999. And that's good enough for us. There we go. So if you take the number 166, punch into your calculator, 166 divide 999 equals, it'll be 0.166166166. And you can easily adapt this to any other fraction you want. So, all right, good. Well, great. In fact, it's a fun mathematical fact that the way we often think of numbers, especially repeating numbers, we can think of it in terms of geometric series. But in general, when we think of decimal expansions, we think of it in terms of a sum, this long infinite sum where it's something over 10 plus something over 10 squared, something over 10 cubed. That's a different part of mathematics, a little bit further down the rabbit hole. Let's look at our next problem. Find the sum from 0 to infinity of 3n minus 2n quantity squared divided by 10 to the power n. Okay, cool. Now, we have to think, what is this? We see things to the power n. That says geometric. So we say, all right, we should be thinking this as geometric. So all right, we're definitely going into this with our geometric hats on. It's not geometric right now. At least not really purely geometric. What we need is like just one thing to the power n. That's what we want, something to the n. So we've got to think of ways to rewrite this. So a lot of the work here is just understanding how can we rewrite this. So all right, we can think of this sum n equals 0 to infinity. If we square the top, well, that would be 3 to the n squared minus 2 times 3 to the n times 2 to the n, then plus 2 to the n squared all over 10 to the power n. All right, now we need to think, how can we rewrite this? Because we don't want 3 to the n squared, we want something to the n. But really, look, what is that? If we think of 3 to the n squared, it's really the same as 3 to the 2n, but that's also the same as 3 squared to the power n. So we could say, okay, that's the same as 3 squared to the n, We'll clean that up in a second here. And minus 2. Now 3 to the n times 2 to the n, we can write it as 3 times 2 to the n. And same thing here as we did for the first term, 2 squared to the n. All of that over 10 to the power n. So let's see what this becomes. Sum 0 to infinity. Of course, 3 squared is really 9. So we have 9 to the power n minus 2 times 6 to the power n plus 4 to the power n, all over 10 to the power n. Now the good news is, if you look at the highest term, right, 9 is better than 10, which is good. It means we've really got a chance for success. Let's break this up into pieces. They might have said, well, what if it was like 11 to the n over 10 to the n? Forget it. Hopeless, right? Because what happens? The numerator is getting huge, and the denominator gets big, but not as fast. The numerator wins the race. That means it goes off to infinity, doesn't converge. But that's a story for another day. Okay, so we're going to think about it. It's 9 to the n divided by 10 to the n, which is 9/10 to the n, minus 2, 6 to the n over 10 to the n. All right, that's 6/10 to the n. And then plus 4 to the n over 10 to the n is 4/10 to the n. All right, well, now break each one of these sums up. So you have sum 0 to infinity of 9 over 10 to the n. And then I can subtract 2, sum 0 to infinity of 6/10 to the n, and then add the sum from 0 to infinity of 4/10. And I really should have taken the time to say, oh, 4/10 is 2/5, 6/10 is 3/5. Now, the fact that you can break things up is allowed as long as you know your individual sums converge, and the individual sums converge because they're geometric converging series, where we know they're converging because they're the r, that ratio, is less than 1. So we do each piece. Our first piece, n equals 0, we get 1. So 1 over 1 minus, we're multiplying by 9/10. Minus 2, here, first term, n equals 0 is 1. 1 minus, multiplying by 6/10, which I'll take advantage and rewrite that as 3/5, plus our first term, n equals 0 is 1, over 1 minus 4/10, which is 2/5. Okay, clear denominator. I'll multiply by 10 over 10 in the first case, so you get 10 over 10 minus 9. Here, multiply by 5, so we're going to get minus. There's already a 2 times 5 makes a 10 over 5 minus 3. And here, multiply by 5 plus 5 over 5 minus 2. So 10 over 10 minus 9, well, that's 10 over 1. So that's 10. 10 over 5 minus 3, that's 10 over 2. Well, that's 10 over 2 is 5, right? Yeah. But don't forget the minus, because I forgot my minus. So minus 5. And then 5 over 5 minus 2 is 5/3. Well, okay, 10 minus 5 is 5, which is really 15/3 plus 5/3, giving us a total of 20/3. And there we go. So this sum, this 3 to the n minus 2 to the n squared over 10 to the n, will add up to 20 over 3. Great. Well, that's wonderful. That's a nice answer, and worked out pretty well, right? Yeah. All right. Well, good. Keep going. Keep going. We're got more problems to do. Well, actually, we got one problem left. One last one. And so let's take a look. A ball drops from an initial height of 2 feet. Okay, so let's, we have a ball. So right now, initially, it's at 2 feet high. And it drops down. Whoop. Okay, now it then bounces to 3/4 of the height from which it fell. Okay, so that means after it hits the ground, it goes back up, not as high up as it started, only 3/4. Now, 3/4 of 2 feet would be about 1.5 feet. And of course now, after it bounces back up, well, it goes back down again. And then it's going to go back up to 3/4 of its original height, and so forth, and so on. So it's going to bounce, 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 bounce. Do, 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 do. So here we go, bouncing all the way. It's actually going to make infinitely many bounces. So the question is, well, how far does it go? Okay, so let's think about the bounces, right? So what's the first part? Well, it started at 2 feet and it went down. So here it traveled 2 feet. Then in the second part, what happened? Well, it's going to go up 1.5 feet and down 1.5 feet. So that's going to be 3. All right, so great. How about the next one? Well, okay, so how can we figure that out? Well, if we think about it, we say, hey, the height up is 3/4 of the height up here, and the height down is 3/4 of the height down there. So it's 3/4 the total of the one before it. So this would be 9/4. And here, same idea, right? You take the previous bounce, and it's 3/4 as long. So it'd be 27/16, and of course the pattern continues. So at every stage we multiply by 3/4. So we can really think of this as 2 plus 3 times 3/4 plus 3 times 3/4 squared plus 3 times 3/4 cubed, and so forth and so on. All right, so we have to add this up. Now, is this geometric? Kind of. We gotta be careful here. Now, technically speaking, as a whole, no. But we say, hey, if we think of it as some pieces, so look, we say, look, there's really 2 parts. There's that first drop, and then there's everything else. And then we say, hey, the everything else is geometric, so we can apply the geometric rule to that part. So the important idea here is, hey, even if the whole thing isn't geometric, if you have one part which is geometric, apply the rule to that part, and for everything else, okay, do something else. Now in our case, the everything else is 2. So we say, all right, great. So now we see what to do. It says, okay, so we're going to have the first drop plus everything else being geometric. Says, okay, we'll have 3, that's our first term, that acts as our A, over 1 minus that number that we multiply by, that R. Well, the R is 3/4, so it'll be 3/4. A over 1 minus R. Well, 1 minus 3/4 is 1/4, which flips over to become 4, and then upstairs. So this is really 2 plus 12, making it 14. And we can even talk about the measurements. 14 feet. And that's the answer. That's how far the bar will go. In other words, in terms of going up and down, even though it will go infinitely many bounces, it will finish the amount of distance it travels after it goes this infinitely many bounces is a finite number, 14 feet. By the way, if you go through and do the math, you can also show that even though you're going to do infinitely many bounces, it's going to be a finite amount of time as well. So the ball doesn't keep bouncing forever. It doesn't bounce infinitely far as it goes up and down. No. It's finite. And this really shows you the interesting idea. It emphasizes, it's possible for some infinite number of things to happen, but complete in a finite amount of time or with finite amount of materials. And that's an important idea. The fact that infinitely many things can add up to finite numbers. It actually goes back, there's a famous paradox that the Greeks thought about, where there was a race between Achilles and the tortoise. And the idea was, all right, the tortoise was very slow. See, Achilles, great warrior. And so they thought, look, we're going to have a race of a mile. We should give the tortoise a 10-foot head start. Okay, no problem. So the tortoise and Achilles set off at the same time. And now, what's the paradox? Well, idea is that Achilles should somehow be able to pass the tortoise. That's true, right? Well, what happens is that before Achilles can pass the tortoise, what does it need to do? It needs to get to where the tortoise currently is. So the tortoise will do the following. As Achilles gets to where the tortoise started, it's moved a little bit. And then it says, okay, well, Achilles now needs to get to there. But in the meantime, it's moved a little bit. And see, the paradox was, hey, the Achilles has to infinitely often catch up to where the tortoise currently is. How can Achilles pass? And so the resolution of the paradox is actually quite simple, which says, yes, it's true that infinitely many things happen, but it can happen in a finite amount, because you can have infinitely many things added together to produce a finite number. It's a really beautiful and interesting idea, and not so trivial. I know doing these problems, it feels like, oh yeah, this is so obvious. Yeah, it's so clean and easy. It's not. It takes time, and you have to think about these things. So I'm glad that you're taking the time, and thanks for joining me, and let's keep working on it. And the more work we do, I know that the better we'll both become. So please, please, please keep working. Come back. There will be more problems to do in the future. So I hope to see you again. Bye.